Welcome to the pre-recording of lecture 10 of MCS 260. So lecture 10, this is the fifth session in our 8-week course. Every session is subdivided in two parts, and this is the second part. This concludes the second week in our 8-week course. It's a lecture that kind of goes a little bit deeper into the hardware, in the how hardware is structured, and we will see a little bit more about the intrinsic operations in Python. So intrinsic means that it is part of the standard library of Python. So in particular, we will see that lists are extremely versatile. We can use lists to work with queues and stacks. So queues and stacks are two major basic data structures. And whether you use a queue or a stack often also guides the program flow, the flow of the data throughout the program. But let's look at some hardware first. So we defined a computer as a synchronous binary digital system. And flip-flops, they are not what you put on your feet, but in electronic circuit terminology, we will see how we can use flip-flops to store data. All right. So another word for flip-flop is also latch, depending on whether you want to emphasize the specific action that goes with the latch, with the flip-flop. So flip-flop is a memory location to store 1 bit. So it's a box. Here we will, in the next slide, we will look what is inside the box. But it is a box that has 3 lines sticking out of it. So there is the input line called D, the data line, and then there is the output line labeled by Q, and then there is the clock line. So a computer is a synchronous binary digital system. So whenever there is a 1 arriving at the clock line, at the line where there is marked with T, then the output is copying what is on the input. So, and unless there is a new value arriving on the clock line, the value will stay there. Okay, so let us look a bit closer what you can do with these flip-flops, or how these flip-flops are being defined. A NOT operation can be realized by one transistor. If you put transistors in series, you get the NOT AND gate. If you put them in parallel, you get the NOT OR gates. So the NOT AND, and the NOT OR are the 3 elementary gates that we realize with transistors. And a flip-flop is a composite, so we could draw it, but that would be completely tedious and cumbersome to draw the pictures that we did last time in lecture 9. Instead, we will define a flip-flop via a sequence of these elementary logic gates. You see here the truth tables, for the operations. So you see what the NOT does, it flips a bit. You see what the NOT AND does, and the NOT OR does. So there is an exercise to actually use the diagrams and to draw the gate that represents the not X nor not Y gate. Or actually, with the brackets, you should see it. It says not Y, then the NOR with X, and then the not of the entire thing. So here is the box. So we can realize flip-flop with one NOT, two NANDs, and two NORs. Again, there are three lines sticking out. Now the lines are very tiny, the box is very big. So we have the input or data line D, the Q, and then the timeline, the clock T. Okay, what is in the box? So here is what is in the box. We have one NOT, two NOT ANDs, and two NOT ORs. So these are the five gates, the five operators, if you like, that are placed like this, and then they are connected with each other. So the NOT is an elementary operator. So here you see now the complete circuit. So we have the data line that connects, that feeds the input to a NOT at the bottom and to the NOT AND at the top. The timeline is the second operand in the NOT AND and in the two NOT AND operators. And then the output goes to the of the NOT AND operators actually goes to the NOT OR operators. I marked the putting of a 1 on the data line. So that's what we're going to simulate. Running through the circuit, so we have a 1 at the data line. If there's no 1 at the timeline, then nothing happens. But here you see there is a 1 at the timeline. If there is a 0 at the timeline also, then nothing will happen. So verify this. If there is 1 at the both NOT AND gates, then it will become a 0. So here you see the latching now of a 1 at the data line. And there is already a 1 at the output line. So we will see that the 1 actually will not change. So we are computing the result of the NOT AND. And now these results are going to be fed to the NOT OR gates. Using the 1 already that is on the queue. So actually you should read this a little bit. So everything happens instantaneously, but we use the fact that there is already a 1 at the output, because this goes to the OR, to the bottom NOT OR gate, that will produce a 0 and will then produce a 1 that will be set onto the output line. So this copies the bit of 1 that was already there. Check what happens. So actually, whether there is a 1 or a 0, so the exercise is here, whether there is a 1 or a 0, it shouldn't really matter. So the not OR is an OR, so 1, 0, 1 or a 0 is a 1. If you negate it, it becomes a 0. So you can immediately see I'm solving this exercise now. If there is a 0 here instead of a 1, then the 0 becomes here and the 0 is also over there. Okay. It's perhaps a more interesting exercise to see what happens when the input is a 0, and you should see that the 0 gets transferred to the output line. In any case, what you should know from this is that you should be able to read a diagram like this and to either write the expression, the logical expression that corresponds to this wire diagram, or be able to see what the circuit computes step by step. All right, 1 bit is already many gates. So here you see what happens now, the evolution in time. So we have, I mentioned that only something happens when at the timeline there is a 1 appearing. So we have a 0 on input and output at the very beginning, 0 at the time. Then at time moment 2, we have a 1 at the data line, but nothing happens because at the timeline there is still a 0. When there is a 1, then the 1 from the input gets copied to the output. As long as there is a 0, nothing happens. But you see that when at time step 5, the input line for the latch becomes a 0, and then the input bit is copied to the output when there is a 1 appearing at the timeline. So this is the evolution in time of 1 bit. Okay, registers are made up by 8 flip-flops. So we have 8 input lines and 8 clock lines. And every flip-flop again stores 1 bit. So this is the first part, so the first 10 minutes. We will let that rest now for a little bit. In the next lecture, I will try to define how the addition of 2 registers actually works. Here is another application before we go to the second part. How to copy 1 bit from one latch to the other. So this can be used to copy registers. Here it is, there is one extra signal there. There is the control signal that signals that the execution needs to happen, copying 1 bit from the output line of the first latch to the other latch. So there is the control signal and the system clock. And they are connected with an AND. So for a time signal to happen, both the system clock and the control signal need to be set to 1. So this is what the AND means. All right, intrinsic operations. So Python comes with batteries included and has a very extensive library. In the last lecture, we had the application of translating a number given in its normal digital representation, and we we spell out the number in words. Here we do the opposite. So in some sense, it's not really that much of an application, but I want to remind you, I want to make sure that if you look at this input-output specification, if you look at this problem statement, that what should really pop into your head is the split operation. So the split operation is a built-in operation on strings. And then with the dictionary, we can look up the value corresponding to the word 40 and the value corresponding to the word 7. So the program is shorter than the program of the last lecture, but still it's a very important application. It's an important repeat of the split, one of the intrinsic operations on a string. The other one is a join. All right, lists. So when you take a data structures class, we spent quite some time on queues and stacks. This slide is to indicate that there is no specific type queue and there is no specific type stack. With a list is so versatile that you can represent both a queue and a stack. So what is the difference between a queue and a stack? In a queue, so think about in a store at the checkout, you have first come, first served. Or when you wait for a bus to get on a bus or get on any public transport, you queue, you get in line. So a queue is first in, first out. In a stack, uh, think about a stack of books, so piled up to each other. To get to the book, to certain books. Books on top of the stack are very easy to get to, but you have to get to the lowest book. You have to remove all the other books. So a stack is first in, so you put a book on this pile of books and then you remove it. So that's also the book that you put in last in, come actually first in. Uh, put in, I'm sorry, first in is last out, or last in is first out. All right. We talk about operations. Operations include both functions. So on a list, you can ask the length of a list. That does not change the list. But you can change lists, and this is where the methods come in. So you can append to a list, and you can remove from a list. You can remove from the front, or you can actually remove from everywhere. So lists are extremely useful. When we are using a queue, we will be appending to the end. When we using a stack, when we use a list as a stack, we will be inserting. The terminology is actually pushing. We push to a stack. But in lists, we talk about appending when we think about appending to a queue, and inserting to the front. Again, the insert comes with an extra parameter here. You can essentially insert everywhere. It's important to remember that if you want to select without modifications, for example, if you want to look at the first element in a list or in a queue or in a stack without removing it, you can do L of not, or L between square brackets not. If you want to look at the last element, see who just added the queue or what is at the bottom of the pile, then you can do the L minus 1, starting counting from the back. Okay, I will illustrate this in a Jupyter notebook. Here are some exercises. So drawing diagrams is not something that you will need to know in this class. Unfortunately, the diagram in the Jupyter lab offers some support, but there are no primitives for the or, for example. You can make a triangle, but then you also don't have the not or. So in principle, you can draw a circle with the diagram, but it will cost you a little bit work. Nevertheless, you will need to be able to translate the diagram into a logical expression. Um, we have seen the realization of a diagram, the drawing. You should also be capable to write this as a logical expression. And I will demonstrate how to solve the last exercise. So a typical application for a stack is to reverse the order. So when we did the conversion algorithm for converting from decimal to binary, uh, 1, 2, 3 in decimal is a sequence of bits, then actually the bits came out in the wrong order. The least significant bit we computed first. So we will push it to a stack. So we will insert to a list. So I will solve this exercise. And it will also explain the right values. Okay, let me go to Jupyter Notebook. I will demonstrate this now by making a new Jupyter Notebook. So we can use lists to represent queues and stacks. So this is kind of the point. The point is also, if you make a new Jupyter notebook, please save it. So these are the intrinsic operations on lists. So I choose a meaningful name. I have two things that I want to show, and I'm showing this because I want to make clear that as a Python programmer, you should actually know this. Appending and inserting, popping. So let me illustrate the operations on a list. So I will make an empty list, and let me append an item to it, one. So it's good practice to have one statement in one code cell, except when it's advantageous not to do so. I will give an application on how you can actually execute loops step by step in a Jupyter notebook. So here we have a list of one element that is sitting there all by itself. So let me append another one. So now I have made a list of two elements. So that is appending. I can insert to a list. So let me insert to the front of the list. Insert the number 3. So these are operations that change the list. So these are operations that are called methods on the list. We can now remove, so the pop, so if I want to see the list as a stack, so it's a little bit more cumbersome. So I have to apply the pop to L, and I get 2 back. And it actually popped the middle element. Very interesting. So what I actually wanted to do, I'm now very curious why this actually happened. Um, Here is something that I want to illustrate as well. We often see our programs, our Jupyter notebook as programs as well. So if I want to restart, I restart and clear all outputs. When I run all cells, it will actually run it as from step to step. So I inserted, And I was thinking that I popped from the front, but that didn't happen. So let me insert 0 so you can actually see that my Jupyter notebook is saying, hey, you did something different. So let me restart the kernel and clear all outputs again. So I'm running all cells. And now you see that actually I get the expected behavior. So I was thinking that I did not need to provide an argument, but if you really want to pop from the start, you must provide an argument. All right, that is appending and inserting and popping. Um, I can pop everywhere, but let me append just another element still here. So I will append to the list as it should have been. I will append the item 3. So I can pop the second item at position 1. So you see I have the item 2 and the list is 1 shorter. I can undo it by insert. So let me say that I'm inserting 5 into the list at position 1. Then that gives me 1, 5, 3. So lists come with operations that allow lists to consider that make lists actually extremely flexible. We select from the list, we um, insert, and we pop or append. What happens if you want to pop an element and it's so another operation is actually the in, so perhaps I should have indicated we used it before. I can check whether an element is there, and actually I can also see if the element is 5 is in there, what is the index. So this gives me 1. If an element is not in there, so let's say 4 is not in there, then it will actually give me a value error. So that is why uh, this test in is very useful. So let me comment this out. If I run this then as a program, it will not generate a value error. Okay, second section, what I want to show is the use of a list. So using a list as a stack. So remember the conversion. So recall, or I will, if you don't recall it, let's consider the conversion of a number in decimal notation into its binary representation as a sequence, as a list of bits. So I will make a list of bits from the number 1 to 3. So this is the number to be converted to binary. And I will make the bit list. Now, if you have to know this, and I will illustrate this again, there is a direct command to compute the string that contains the bits in there. So there is a much quicker way to do this, but let's illustrate the stack. So what does the algorithm do? It computes the division and it does a division and computes the quotient and remainder. So we can do this all in one statement with the div mod. We divide by 2 because 2 is the base. We have the remainder, r, and n is the quotient. So 128 is 2 times 123. So 123 is 2 times 61 plus 1. So that's what this calculation is. I will insert, so push to the sack, the remainder. So 1. So now I have to continue doing this until the quotient becomes 0. Um, so let me show you how to do it. So this will involve a lot of typing, but I will type the instructions in a code cell. So I will compute the remainder and replace n by its quotient. So I will print the bit string and I will print n. So typically it's not such a good idea to have too many statements in one code cell, but here it is extremely convenient because by running this, so I run it once, you see that 1 bit was added because 61 is 30 times 2 plus 1. And now I will run it again. And now 30 is an even number. So it got replaced by 15 and the remainder is 0. So I inserted 0. Let me run that again. So now I'm at 7. I still have to continue. Run it again. 3. It's not yet 0. And then run it one more time. And now I have the bit representation of the um, binary representation of the number 1, 2, 3. Just to verify, how do you do this real quick? Well, you make a string if you want to see the same thing happening. So here you see the string, and I make the list of bits from this. So actually you can do this in one statement even for C in bin 1, 2, 3. So that will give me the list of bits, but I have to select from it. So my um, final result is I have to slice, bite off, start at 2. So if you like, you can do everything in one line with a list comprehension using the bin statement, and then follow it by 2 columns. But the point I want to make here, actually, of this section, so it's the same point. So lists come with intrinsic operations, functions, and methods that allow you to be very productive. So if you want to list of bits in a bit string, you can either use this to illustrate the algorithm, use a list as a stack, or you can select from this. Okay, so let me go back to the slides. So what I actually have solved is the last exercise. So we will use a stack, and you can illustrate this. If you submit this exercise, you can submit this just with the example that I have picked, but it's good practice to actually also run this on a different number. Okay, so I will post the Jupyter notebook that I have prepared here. It contains a little bit more information. So remember here that some methods not only change, so the pop, perhaps I should have emphasized this a little bit, the pop works both as a method. It changes the list on which it is applied, but it also acts as a function. So it returns something. All right. Let's now go to the third part. So here there is the exercise write values. Let me go back to what write values is supposed to do. Here is the input output specification. So we have a number that is spelled out in full, and actually 42 is a better number in a computer science course. So we prompt the user for a number in words, and then with the dictionary lookup and an addition of the 40 and 7, the numerical value is computed. Okay, so I have prepared this so I can bring up the correct program. I ask for a sequence, so giving a number of words. So actually, let me first run this. So Python write values, and I made a spelling mistake. So I said that 42 is actually better. So 42 is written out as the digits 4 and 2. So what does this program do? It captures a string in the words, and it is going to get these words, and actually if a word is in the dictionary, so actually this is an important point here. So I illustrated the in for a list. The in is also used for a dictionary. Let me illustrate this. So how can you do this? So to save myself a lot of typing, I will copy this. I will let me do the application here. So I will using a dictionary. So I will paste this back in. So this is my dictionary of the words, and I can check if, say, the word 40 is in the dictionary, and everything is capitalized, and it is true. So this will prevent when I'm have a misspelling. So English is kind of, so first of all, you have to provide, so I can now do 40, but then I have to do some effort to spell it right. So I will have the key error. So if, say, so there is no 4, so there is a key error. So this will generate a key error. So let me document this note. So this is the usefulness of the in. So what I want to do with this program is that the program actually should not crash. So it may be that the user types in 40, and then we can immediately terminate. So it is a simply dictionary lookup. If the user types in 100, it's a complete lookup. Otherwise, with 42, it will be splitted on the space, and then we will look up the values. So the outcome will be the numerical values, and I will take the sum and then the string representation of the sum. So also here, So let me document how this program works. So I just ran it at the terminal prompt, but you don't really get too much out of this. So let me say that the input, so the data that I'm getting is 42. So that's my input. I will split it. So the splitted string will be a list. So we split on the space. So splitted is now a list. So I have 40 and I have 2. So the statement was rather dense. So what I did is I took the dictionary, split it 0. So let me unravel this. I have the dictionary split it. So sometimes we see the complexity as a program as a number of lines. But if you like, a better way to work with this could be to use separate names of the variables. So what I did is that I'm computing the sum of these two numbers now. So let me also copy and paste. So I'm computing the sum, and then I'm taking the string representation. So the outcome was the string data plus is plus the string representation of the 42 now. And I don't want to select this, so let me assign this to something. The string of the number. And then I can print the output. So notice on this Jupyter notebook now, in cell 50 you see a plus, and in the code cell 51 you see two pluses. Now the pluses in cell 50 are the arithmetical additions of the numbers 40 and 2. The pluses in the operation in the execution cell 51, they are the string concatenations. So they also are plus, but they are not the arithmetical pluses. So they just add things together. So I hope that this explains this statement here. So we also have the plus equal. So the plus equal will take outcome. So outcome is actually just a bit longer, the value of what the user types in. I will add to the outcome the string representation of the sum. I could also have worked with a format string. But the string representation is kind of neater in the sense that we are taking numbers, converting them into strings, or taking strings and looking and using them as the keys. So it's important. So here we take the raw input. So here raw input is in Python 2 terminology. We take what the user gives us, the words here assigned to the words, and we use the words as keys in the dictionary if the word is already there, if the word is already in the dictionary, then we are done. Otherwise, we will split on the spaces. Okay, so you can say, well, this is a shorter program, but it's actually not really the reverse of what we did with the right numbers, because what happens when the user types in 100? What happens then? So, and that is the exercise. Let me go back to the end. So I have given you the beginning of the program that is the inverse of the right numbers of the previous lecture. As an exercise, I want you to finish this. Think about all the cases that you will need to deal with. So if you have 400 and 313, it takes a lot of splitting. So you have to be careful where the and is coming in. You have numbers such as 100, but then you also have 42. Um, so, uh, and there is of course always the number 0 that we can already handle. So for the previous lecture, for the entire algorithm, I drew a flowchart. It's actually also very good when you extend this. So I do not think that, no, you do not need to extend the dictionary. The dictionary is fine, but you have to be a little bit careful. So the base case remains if the word is in the dictionary, which means that it's only one word, and it can immediately um, be used. And so you can also assume that the user types in everything correctly, everything lowercase. Although if you want to make your program more robust, we've seen what happens here, so you can actually normalize and translate everything to lowercase. There are stripping of spaces, of leading spaces and trailing spaces. So we didn't cover this, but you can see this is also an intrinsic operation, which is useful to make your program more robust. Okay, here in this lecture, I'm not going over time, although I could babble a lot more. This concludes the second week of the 8-week summer session. We started with the definition of an algorithm, an ordered set of unambiguous steps that can be executed, executable steps, and in a process that terminates. Central in the discipline in computer science, which transforms information. Python is really very well suited to transform information. So here, numbers given in words can be translated into uh, decimal notations or internally in binary. Okay, I will stop here. The next lecture will introduce loops.